Hi everyone, I'm Jaemin from KAIST School of Electrical Engineering. Today I'll talk about our recent work on model selection for self-supervised anomaly detection. Before starting, I am a researcher working on the field of data mining. So if you heard of the word, data mining is a field to understand data and to find patterns from it, and to use these patterns to do some useful things in the world. So many data mining tools use machine learning and deep learning tools like deep learning models like the neural networks and convolutional neural networks, as you might heard of it. But we focus on problems and applications as a data mining researcher rather than the models. So that's a little difference from the people who are working on machine learning, because I do data mining. So if you see the slide, there is a brief overview of my research field. So data mining and machine learning has some significant overlap, and also an overlap with deep learning also exists in the figure. So I'm at the middle of the three research fields as an AI engineer. So as a researcher, my goal, which is a little different from today's topic, is to design robust and generalizable graph neural networks for real-world graphs. So I work on data structure called graphs, which is designed to model the relationships or the interactions between entities in the world. Like I design probabilistic approaches that enhance graph neural networks, or I develop methods for self-supervised learning and graph augmentation like that. So although my main expertise is in graph structure data, recently I started to work on anomaly detection, which is a fascinating research field, which is also related to my research field. So this slide is just an overview of myself, and I'll move on to the real topic that I'm going to talk today. So this is a simple outline of today's talk. Anomaly detection, as its name implies, is a problem to find anomalies from data. When we say anomalies, we often refer to some data that are different from most of the data samples in the data set. And these anomalies are common in many real-world data sets, as you can see from these figures. Like in a time series, there are always anomalous observations in a long time series. And if you see that a set of fishes, then there is a red fish seeing the other direction from the other fishes. And in a two-dimensional space, as shown in the rightmost figure, there are some outliers or noise or anomalies that are separated from the normal data. So finding these anomalies is essential to improve the reliability and efficiency of the system, and even to improve the accuracy of the system, because these anomalies act as some noisy information that prevent our model to perform really well on the system. So anomaly detection is hard because there are no labels of anomalies, which means how to define anomalies depends on our applications or the purpose of an engineers. So traditional approaches on anomaly detection rely on unsupervised learning, which refers to a machine learning paradigm where there are no specific labels to train our model. So this is how to do anomaly detection without labels in a typical manner. So you first find the probability distribution Px from a set of mostly normal data, and then we say that a point is anomalous if that point is far from the center, which means its likelihood or its probability is quite low compared to other samples. And this approach is also known as density estimation, because we aim to estimate the density of the normal data in the space. But it has some limitations because it is a traditional approach, which means we need a lot of data samples to accurately learn the data distribution Px. And this is problematic, especially with high dimensionality, because if we are going to fill in the n-dimensional space, then we need a lot of data samples where the number is proportional to the exponential of the dimensionality. And this phenomenon is also known as the curse of dimensionality, and that is the reason why it is hard to design an efficient density estimation method for high dimensional data. So as you can see from these figures in this slide, as the number of dimensionality increases, it seems like the data are more scattered and sparse in the space, which means we need more samples to fill in the space. So our purpose, our motivation to do self-supervised learning is to avoid filling in the whole space by finding a lot of data samples. So we can say that self-supervised anomaly detection, or simply SSAD, is the future of anomaly detection. So the idea is we train a classifier or any model that can detect pseudo-anomalies from the inliers. Put differently, we aim to train a classifier that can detect the artificial differences between samples. In the figure, we are given an image of a normal butterfly, and we can apply different data augmentation functions, which I refer to FAUG, to create different types of butterfly images with different characteristics. As you can see, these images are quite different from the normal image, but they still look like butterflies. So we can say that they are more plausible anomalies, although they are created artificially from ourselves, and we can treat them as anomalies, and we can learn a classifier that can separate our normal butterfly images from these augmented samples, which we call artificial anomalies or pseudo-anomalies. So why is it better than the unsupervised approach? Why does it allow us to avoid creating a lot of samples to fill in the space? Because SSAD allows us to focus on a plausible subspace of data, which seems a little hard for non-experts. But this is quite simple, which means it is okay to create a few possible types of pseudo-anomalies to train a classifier. We don't need to consider the whole d-dimensional space, because in the space, like most of the samples in the space are not feasible. We don't have to consider them when training our classifier. For instance, when we want to train an anomaly detector on these butterfly images, then we don't have to consider this white noise as a possible anomaly, because it is obvious that they are not like any butterfly images. So instead of trying to fill in the space by considering this like a lot of non-feasible anomalies, we want to focus on plausible anomalies, which are created by data augmentation functions. So this is a better comparison between the density estimation and self-supervision. Density estimation is like a filling in the space with dots, which are data samples, while self-supervision can be understood as drawing many boundaries around the data in the space, so the resulting model can be less sensitive to the data dimensionality, and it becomes less efficient when the dimensionality increases, but we can say our framework is less sensitive, much less sensitive compared to the density estimation. So, but SSAD is good, but still it has some limitations, and one of these limitations is that it has many important hyperparameters, because the choice of the augmentation function FAUG determines the decision boundary that we draw in the space, and then it will determine the effectiveness of our whole framework. So including the choice of the function, a lot of hyperparameter choices largely affect the success of SSAD. However, unlike in many other machine learning fields, model selection is especially challenging for SSAD because the problem is unsupervised, which means we don't have any labeled data to validate whether our hyperparameter settings are good or not. So our question is, how can we perform hyperparameter search on SSAD without having any labels? So this question is quite hard, and it has never been answered in the literature, because it feels almost impossible to do hyperparameter search without relying on labels. So from this slide, I'll introduce two of my recent works for that question. So in the first work, we focus on transductive anomaly detection, which means, if we don't have any signals to train our classifier, then we cannot solve the problem. It is impossible. So we need somehow some information to train our model and to validate whether our hyperparameters are good. So we focus on the transductive setting, which means we are given normal only training data, dtrain, and we're also given a set of detectors trained with FAUG, like augmentation functions with different hyperparameters. So the information 1 and 2 are the same as before, but we also assume that we are given unlabeled validation data, dval, containing normal and abnormal data. So the fact that we are given this validation data does not hurt our problem setting, because it is still unsupervised, and it is very common that unlabeled. So it is very common that unlabeled data are given in the training time, because it is okay to gather this data if you don't have to rely on getting those labels. So So our goal is, given these three types of information, we want to find a loss function so that we can tell which detector is the best or not from the given set of detectors by relying on this loss function. Or we want to say that our detector is best because it minimizes our loss function. So this whole work is about designing this loss function without relying on labels so that we can evaluate each detector model given the set. Then how can we do that? Our motivation is, let's utilize this unlabeled validation data dval to design the loss function. So let fgen, which looks similar to fawk, be a function that generates anomalies from normal data. So fawk is to train an augmented data from normal data, as shown in the slide, but fgen is a function that creates true anomalies from data. So fgen, although we know that there should be this function fgen in the data set, but we cannot access this function because that is some hard to calculate function that only we can assume that it exists and it will create this anomalies. So suppose that our augmentation function aligns well with this fgen, which is an anomaly generating mechanism, then we can expect the following to be true, which means the union of dtrain and daug should be similar to dval, because in the dval there are normal data and abnormal data at the same time. So although we don't know the exact boundary between the normal data and abnormal data in the validation data, but still we can expect their union will be similar to the union of ftrain and fawk if fawk and fgen are aligned well. So this is a crucial motivation to design our loss function. So based on that idea, let's approximate the alignment between fawk and fgen based on the distance between two sets. One set is a union of gtrain and gawk, and the other set is gval, based on our previous motivation, which is straightforward. Here, alpha in the equation is a set of hyperparameters which we want to evaluate, and d is a distance function between different sets, and g refers to the set of embeddings created with hyperparameters alpha. We use z instead of the raw data because, as we all know, raw data are very high dimensional and sparsely distributed in the space. So if we have a good embedder or a good machine learning model, then we will compute the distance on the embeddings, not on the raw space, raw data space. So here we expect that smaller, this loss function, L tilde, represents that a hyperparameter setting alpha makes a better alignment. Or in other words, we want to find the detector model that minimizes this loss function or the distance between these two sets of embeddings. So this is a slide, some of the experiments that we show in the paper. In here, we compare our loss function DSP with other unsupervised model selection approaches. Some of them are very naive, such as, for instance, average means the average performance of different hyperparameter settings, or rand means we randomly select a hyperparameter without having any prior knowledge. So here we can see our proposed loss function DSP outperforms all competitors in 6 of the 8 cases, which is a great result that shows that our method is quite effective to select the best hyperparameters for unsupervised anomaly detection. So please refer to the paper for more detailed results and detailed analysis, but I'll move on because we don't have enough time in this talk. So in the second approach, we tried to improve our previous method by making the model work on end-to-end setting. So the core limitation of the previous approach that I just introduced is that it works as an offline evaluation measure, which means we need to train all possible N models before doing selection, and then the loss function supports selecting the best model from the set only when the training is done for all models. So it can be effective, but it is time consuming, at least in terms of the resources, right? So our question is, how can we design a framework for end-to-end learning so that we don't have to train all these different models before doing the selection? So for doing that, we need a whole lot different framework that consists of 3 different components. The first one is a differentiable validation loss that measures the alignment. So it should be differentiable because we are going to train our model in an end-to-end way, unlike in our previous method. And the second one is on differentiable augmentation functions based on the same reason, because we want our augmentation functions to to be differentiable to propagate the gradient even to the model. And then lastly, we need an implementation technique that makes everything possible. So the first one, I just didn't include the equation because it makes harder to understand the idea. But here I just showed the property of our loss function that we proposed to be differentiable. So here in the figure, let's say we have two values of hyperparameters u1 and u2, and the arrows represent the direction of the negative gradients. If you see this figure, if we know that the optimal space is when the u1 and u2 are both 0, then we can say that the negative gradients nicely point to a local optimum, which shows that our loss function is not just differentiable but also works in a way that we expect, which means by minimizing this loss function, we can find the best hyperparameters as shown in the figure. Then, in fact, many existing augmentation functions are not differentiable because they are not designed to be differentiable. I mean, their goal is not about differentiability. So what I did is I made a differentiable, our own version of our augmentation function based on a previous augmentation function. So if you see this figure, there's a very simple augmentation function called cutout, which just removes a small patch and replaces the patch with a black pixel. So we can obviously say that the images created by cutout are anomalous, right? Instead of making that rectangular pixels which are not differentiable, we created a smooth, differentiable, like a circular shaped patch, so that our augmentation function based on works based on the hyperparameters in a differentiable way. And then based on these two components, we designed a framework that allows us the bilevel optimization for theta and A. Here, theta is a set of parameters for a detector which are also a target to learn, but not the main target of our whole framework. On the other hand, A is a set of hyperparameters for FOG, which is our main target to learn in the hyperparameter setup. So we aim to train both theta and A at the same time for the bilevel optimization, so that we can find the best hyperparameters A based on the best models of theta. So the update of A and the update of theta are done interchangeably. So as a result, we hope they converge to a best local optimum so that we know what are the best hyperparameters and what are the best parameters for our case. So instead of showing these numbers, I just have this slide that shows the qualitative result of our framework. So there are 4 figures, and at each figure, the left part is an actual anomaly and the right part is an augmentation function that we have learned through our framework. So by comparing these 4 types of figures, we can see the actual anomalies have different shapes and different sizes and even different length from different normal images. But as a result of applying our framework to these different types of anomalies, we are able to successfully replicate the anomaly generating mechanism by finding a good augmentation function. So by doing this, we know that our pseudo anomalies are aligned with the real anomalies, so that our whole motivation for the previous approach or even for this approach works very well. And one thing to note is that we don't give any labels in the process, which means they are learned from themselves from unsupervised validation data without relying on any labels or any abnormal data labeled in the training set. So that was all for today's talk, and I just introduced 2 of our recent works for the unsupervised anomaly detection based on hyperparameter search. So we know that hyperparameter tuning is important for all machine learning models or all machine learning approaches. And what I wanted to say is hyperparameter tuning is even more important for SSAD because the problem is unsupervised and the effect of any framework is largely affected by the choice of hyperparameters. However, the bad news is the problem is largely underexplored, maybe because just people don't have any interest in this problem, or people think that this problem is too hard to solve in the research. But I just hope more people to get interested in this topic, because a good hyperparameter search allows us to apply our good model to actual anomaly detection scenarios. Because if you don't know how to select our hyperparameters, then it is even harder to apply our models to the real world cases. So in this talk, or in our recent work, we have proposed an offline and an end-to-end method for solving the problem with these amazing collaborators, mainly from CMU. And here is the list of references for the talk. So you can just refer to these papers if you are interested more and if you want to see more detailed results. So that's it. Thank you for listening.